Hi friends, I am Mohan, studying in Sri Venkateswara College of Engineering, Information Science and Engineering. My USN is 1E22IS032. Today I am going to explain about properties of groups, subgroups, which comes under the DMS called Discrete Mathematics Structure. Let us discuss one by one. Introduction to groups. A group is a set combined with an operation that satisfies certain axioms. The operation must be closed, associative, have an identity element, and every element must have inverse. Groups are fundamental structures in abstract algebra with applications across various fields. Group axioms. The closure property states that performing the group operation on any two elements results in another element from the same set. Associativity means that the grouping of elements does not affect the outcome of the operation. An identity element in a group is a unique element that leaves other elements unchanged when combined. So the axioms of a group theory says that a set of G of element with an operation which satisfies the closure. If G1 and G2 belongs to capital G, then G1 and G2 also belongs to capital G. Associativity, we always have G1 into G2 into G3 is equal to G1 into G2 into G3. For third one, the existence of identity element, an element 1 exists such that G into 1 is equal to 1 into G is equal to G for all elements G of capital G. Existence of inverse element for each element G of G, and inverse element G is to 1 exists such that G into G minus 1 into G is to 1 into G is equal to 1. The simple set of axioms leads to an amazing rich mathematical structure. Inverse in groups. For every element in a group, there exists another element that combines with it to yield the identity element. This property ensures that every operation can be undone within the group structure. The existence of inverses is crucial for the stability and functionality of the group. You can see that group 4 and group 5, which comes to the inverse, is crucial for the stability and functionality of the group of a structure, which the property ensures that every operation can be undone within the group structure. Types of groups. Types of groups in an organization is a formal groups and informal groups. In formal groups, there are command day groups, task groups, communities, interest groups, friendship groups. In informal, silicues, subsilicues, sales classification of group. In sales classification of group, there is a four types. First one is apathetic groups, erratic groups, strategic groups, conservative groups. So groups can be classified into various types such as finite, infinite, abelian, and non-abelian groups. Finite groups have a limited number of elements, while infinite groups have an endless number. Abelian groups are commutative, meaning the order of operation does not affect the result. Subgroups. A subgroup is a subset of a group that is itself a group under the same operation. For a subset to be a subgroup, it must satisfy all the group axioms independently for the larger group. Identifying subgroups helps in understanding the structure and behavior of the larger group. Group is a subset of groups which comes under the subgroup of group. Criteria for subgroups. The non-empty subset must contain the identity element of the parent group. It must be closed under the group operation. Combining any two elements must result in an element of a subset. The subset must also contain inverses for all items elements to qualify as a subgroup. Note, all subgroups must contain the identity element. You can usually write down subgroups by trial and error. For example, 0, 1, 2 will not be a subgroup because 2 into 2 is equal to 4. So 0, 1, 2 won't be closed. Here you can see the example of proper subgroups are 0, 2, 4 and 0, 3. And G, capital G itself are trivial subgroups. So in all there are 4 subgroups of G. The trivial and whole subgroup. The trivial subgroup contains only the identity element of the group. The whole group itself is always a subgroup of itself. These two subgroups are essential in group theory as they serve as boundaries for subgroup classification. Properties of subgroup. Every subgroup is itself a group that adheres to same operation as the parent group. The intersection of two subgroups is also a subgroup. A union of two subgroups, however, is not necessarily a subgroup unless one is contained within the other. Lagrange's theorem. Lagrange's theorem states that the order of number of elements or the order of a subgroup divides the other of the group, and this theorem provides critical insights into the structure of finite groups. The- It highlights the relationship between the sizes of groups and their subgroups. Lagrange's theorem. If G is finite group and H is a subgroup of G, then H divides G. The number of distinct left closest of H is G. A coset is a form of partitioning a group into equal-sized subset based on the subset. Left coset and right coset can be formed by multiplying a subgroup by element of the following group. And cosets play a crucial role in understanding group structure and in the proof of Lagrange's theorem. The first major fact about cosets now follows. Let capital G be a group and let H be a fixed subgroup of G. Theorem 1 says that the family of all the cosets H and a ranger over capital G is a partition of G. Proof, we can say that first we must show that any two cosets, say H and A and HB, are either disjoint or equal. If they are disjoint, we are done. If not, let X belongs to HA and HB because X belongs to HA where X is equal to HXA. For some H1 belongs to H because X belongs to HB, X is equal to H2B. For some H2 belongs to H. So thus H1 is equal to H2B, and solving for a, we have A is equal to H inverse into H2B belongs to A belongs to HB, where it follows from property 1 and above H is equal to HB. Next, we must show that every element C belongs to G is in one of the cosets of H, but this is obvious because C is equal to EC and E belongs to H. Therefore, C is equal to EC belongs to HC. Thus, the family of all the cosets of H is a partition of G. A normal subgroup is one where the left cosets and right cosets are identical for all elements of the group. Normal subgroups allows for the formation of quotient groups. They are essential in constructing group homomorphisms and understanding group actions. Definition: a subgroup N of a group G is said to be a normal subgroup of G, and G N and G inverse belongs to N for all G belongs to G and N belongs to N. Equivalently, if G N and G is to 1 is equal to G n G to the power of minus 1 and N belongs to N, then N is a normal subgroup of G if and only if Gn belongs to N where N is equal to for all for G belongs to G. Quotient group. Quotient groups are formed by partitioning a group into cosets of a normal subgroup. The operation on the quotient group is defined using the operation of the parent group. This concept is vital for simplifying complex group structure. The the homomorphism is a functional between two groups that preserves the group operation. They allow for the compression and analysis of different group structures. Homomorphisms can help in identifying isomorphic groups which share the same structure. Homomorphisms. Definition: if G and G are groups, a function from G to G is called a homomorphisms. If it is a operation preserving, so that is for all A comma B in G, where AB is equal to A comma B. Example: every isomorphism is automatically a homomorphism, but not conversely. If R star into R star given by X is equal to X square a homomorphism, it is an automorphism. And R plus into R plus given by X is equal to X square is a automorphism. R into R given by X is equal to X square is a homomorphism. Note that for any pair of groups G and G, there is always the least homomorphism between them. We can discuss what it is. Isomorphisms. Isomorphism groups have a one-to-one correspondence that preserves group operations. If two groups are isomorphic, they are structurally the same, even if their elements are different. Recognizing isomorphisms helps in classifying groups based on their structures rather than their element. Isomo- Isomorphic groups. Two groups G and G are called isomorphic, and if there is a one-to-one correspondence between their elements, G is equal to A, B, C up to P, and G dash is equal to A dash, B dash, C dash up to P dash, where A is equal to A dash and B is equal to B dash, AB is equal to P, A dash, B dash is equal to P dash. Example D3 is isomorphic to C3 and rotation by reflection of the plane. Group actions. A group actions describes how a group operates on a set, providing a way to analyze symmetries. It can be used to satisfy the study of relationship between groups and geothermic objects. Group actions are instrumental in various mathematical areas, including geothermic and combinators. Cyclic groups. A cyclic group is generated by a single element with all other elements expressed as a powers of this generator. Cyclic groups can be finite or infinite dependent on the properties of the generator. They are among the simplest and most studied types of groups. Abelian group properties. In an abelian group, the order of operation does not matter. Every element commutes. Abelian groups are easier to analyze and often exhibit more straightforward structures. Many fundamental results in a group theory applies specifically to abelian groups. Applications of group theory. Group theory has applications in various fields, including physics, chemistry, and computer science. It helps in understanding symmetry, which is crucial in molecular structures and crystallography. In computer science, group theory assists in cryptography and coding theory. Conclusion. The study of groups and subgroups is essential in abstract algebra and mathematics as a whole. Understanding these concepts provides a fundamentation for advanced mathematical theories. Groups and subgroups have broad applications that extend far beyond pure mathematics. So this is about the groups and subgroups.